Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 4 for October 2024. Let's begin with the first question. In question 1, an ester has the structure which we see here. They say which pair of reactants would form this ester under suitable conditions. So for an ester, the part that could come from a carboxylic acid or an acyl chloride is the one attached to the carbon, or is the one with the carbon-oxygen double bond. So if we count the number of carbons, 1, 2, 3, 4, so it could be butanoic acid or butanoyl chloride. In the other side, we have 1, 2, 3 carbons, so the oxygen is at the end, so propan 1O. So the answer is B, butanoyl chloride and propan 1O. In question 2, they say which compound has the highest boiling temperature. If we look at these compounds here, this one only has London forces, this one has no hydrogen bonding or no intermolecular hydrogen bonding. The same goes to this one. So it's only D that can form intermolecular hydrogen bonding. Now all these have similar London forces because of the number of electrons, but because D can form intermolecular hydrogen bonding, it's going to be the answer. The steroid nandrolone has the structure we see here. They say how many chiral centers are present in nandrolone. If we look from this side, this is not chiral because there is a double bond, that's not. This is not 2 hydrogens, here 2 hydrogens, but here there is a hydrogen and 3 other different groups. So this is chiral, that is chiral, this is not because there are 2 hydrogens here, 2 hydrogens. This is chiral, there is a hydrogen and the 3 different groups. Here we have a hydrogen and 3 different groups. And here we have a methyl and 3 different groups. Here we have a hydrogen OH and then the 2 groups attached. So we have 1, 2, 3, 4, 5, 6. The answer is therefore A. Next they say nandrolone is broken down in the body into a compound shown here. They say what reactions have taken place to form the new bond at position 1 and position 2. If we go back to compare with the structure, at this position we had a carbon-oxygen bond, and it's been converted from an ketone to an alcohol, meaning a reduction has occurred. So reduction from a ketone to an alcohol, which is a secondary alcohol. In this side here, the double bond has disappeared because hydrogen has been added. Basically, it's an addition reaction. Some people could also call it reduction. So the possible answers here are reduction for this. Since there is no reduction here, but they've put addition, then this part matches, and so the answer is going to be B. Next they say a sample containing 2 × 10⁻⁹ gram per centimeters cubed of nandrolone was analyzed using gas chromatography, and the chromatogram produced is what we see here. So we have the absorption and then the retention time. Then they say a second sample containing 4 × 10⁻⁹ gram per centimeters cubed of nandrolone was also analyzed using gas chromatography under the same conditions, which is the chromatogram produced by the second sample. Since we have the same solvent, this is going to be at the same retention time, but the concentration is doubled from that to that, so the peak is going to be higher or twice the original peak, and that's why D is going to be our answer. In question 4, they say a titration curve for the titration of an acid with a strong base is shown. We can see that. Then they say what could be the formula of the acid. In this case, since we see 2 vertical lines, it means it has 2 hydrogens, so H2X should be a suitable answer. It's a diprotic acid. Then they say ethanoic acid, which is that can react with a hydrogen sulfide ion, which is the correct acid conjugate base pair for this reaction. If this is reacting with that, it means this is giving away the proton, and therefore it's going to be the acid, and this will be the base in the forward reaction. And to the product side, this is going to form ethanoate as its conjugate base. So the answer is going to be ethanoic acid as the acid, and then ethanoate as the conjugate base. You can see this here. So the answer is going to be a C. In question 6, they say which indicator can be used to show the endpoint of a titration between hydrochloric acid HCl and ammonia solution. So because this is a strong acid and this is a weak base, methyl orange will work good, so I chose methyl orange because the pH changes between 3.2 to 4.4, which is appropriate for this titration. In question 7, phenolphthalein is a very weak acid and it forms a colorless solution under acidic conditions. Sodium hydroxide is titrated against hydrochloric acid using phenolphthalein indicator. At the end point, the solution is pink because phenolphthalein. It's going to be pink because phenolphthalein is going to donate a hydrogen ion, meaning it's acting as an acid, and in that process it becomes an anion, so D is the suitable answer. Then in question 8, the dissociation of water is an endothermic reaction, as we can see here. They say, what is the best estimate of pH at 313 Kelvin? Now they've given us the different kWs at 25 or 298 Kelvin and at 313 Kelvin. This means in our calculation we're going to use this one here. So we know Kw is the hydrogen ion concentration times the hydroxide ion concentration. Since we are using this value, it should equal to that squared. Since these are going to be coming from the same water that is dissociating, their concentration is going to be the same. So this is H plus squared. Then to find the concentration of hydrogen, get the square root, and then pH will be the negative log of that, giving us 6.767, which is approximately 6.8, and so the answer is C. In question 9, magnesium nitrate decomposes on heating as shown here. What is the expression for the equilibrium constant Kp for this reaction? Kp takes into account gases. Since this is a solid and that is a solid, they cancelled out. So Kp is going to equal to the partial pressure of NO2 squared times the partial pressure of oxygen per a half. And so the answer is A. In question 10, which test can be used to distinguish between each of the pairs of compounds shown? This is an alcohol and a carboxylic acid. Here we can react with sodium carbonate. The carboxylic acid gives us carbon dioxide, and there is no observable change here. So B says add sodium carbonate, and that should be the perfect answer. Then here we have a primary alcohol and we have a secondary alcohol. But the difference is the secondary alcohol has a CH3 here, meaning we can use iodine in sodium hydroxide because iodine is going to cause the oxidation of this into a ketone, and then we will have a CO or a carbon oxygen double bond attached to a CH3, and so that is going to give a positive test with the iodoform test. So the answer is C, warm each compound with iodine under alkaline conditions. And here we have a ketone and an aldehyde. Here we can use Tollens reagent because this is going to give us a positive result, but there will be no observable change here. So the answer is warm each compound with Tollens reagent. Here we will see a silver mirror and there will be no change here. Next, they say some thermodynamic information is shown for 4 reactions W, X, Y, and Z at 298 Kelvin. Which of these reactions are feasible at 298? So I'm going to use, since they've given us delta H and TDS for the system, I say ds total equals 2ds system minus delta H over T, where this is the surroundings. So to make TDS the subject, TDS, meaning multiply through by T, this is TDS total should equal to TDS system minus delta H. Now we know for this reaction to be feasible, this is going to be positive. So we get a value that is going to give us a positive thing. If delta H is negative, meaning this part here is going to be positive because a negative times a negative gives us positive, and this is positive, we see X is going to be feasible. And then there is another way here when they say negative and with a large negative value than TDS. So this is also a possible scenario given the TDS system is negative. That is also going to be feasible. So the possible answers are W and X. If you substitute in this, giving us a positive value here. So in question 12, they say which isomer has the most peaks in its carbon-13 NMR spectrum. The first one has this and that are identical, and then the remaining 4 are also identical. So this has only 2 peaks. For this one, if this is the first peak, 1, 2, 3, identical, then second, which is different from the first 3, and then third and fourth. So here there'll be 4 peaks. This one here is going to have 1, 2, 3, 4, and then these 2 are identical. So those are 5 peaks. We have 1, which is identical to that, 2, which is identical to that, and 3, which is identical to that. So here we'll have 3 peaks. So the one with the most peaks is going to be C, 5 peaks. Next, they say ethanoyl chloride reacts with ammonia, forming ethanamide, as we see here. The first step of the mechanism forms the intermediate shown. So they say which diagram shows the movement of electron pairs when the ethanamide forms from this intermediate. So these electrons are returned to form the double bond. This goes away, and then this breaks away to return the lone pair onto nitrogen. So A is going to be the answer. This one returns the double bond, that breaks off, and then this bond returns the electrons in the bond towards the nitrogen, regenerating the lone pair on the nitrogen. The others are all wrong. For example, this Cl has to leave, this is out. In this case here, let's see, this one has to return the electrons from the bond, so that is out. And here is the electrons moving towards the bond, that is also wrong. In question 14, the compound shown reacts with excess LiAlH4. This is a reducing agent. They say what solvent is used in this reaction? It should be ether. We usually write dry ether, so B should be the answer. In part B, which is the organic product that forms, this is a carboxylic acid that is going to be reduced to convert it into a primary alcohol. There is no reaction with this, so the answer here should be D. And in question 15, which monomer could form a condensation polymer without needing a second type of monomer? Here the answer is going to be B. There is no reaction for A if there was one molecule like this and another molecule, OH and OH will not react. This also will not react with a similar molecule, and that won't. So here we have an acyl chloride on one side and an OH on one side. So an ester bond is going to be formed, meaning there is a possibility of forming a polyester. In question 16, an ester X with a molecular formula carbon 8 hydrogen 16 O2 has the structure shown below, which is this one here. They said it is the name of the alcohol used to synthesize X in a reaction with ethanoyl chloride. So in this case, if this is the ester, this part comes from the ethanoyl chloride, this part here, and this other part should come from the alcohol. So the alcohol is drawn here, and we try to name it. We see either side, this is carbon 3. So we have 3-methyl pentan 3-ol. So that's the answer. And in part B, they say one of the proton environments in X is labeled A, which is this one here. Complete the labeling of this structure to show each of the other proton environments in X, clearly linking any that are the same. So this environment and that environment are the same. I label them B. Then we have this and that are the same. We call them C. And this is farther away from the rest. It's going to be D. And then next they say describe 3 ways in which the high resolution hydrogen NMR spectrum can be used to distinguish between the methyl group in X other than A. So if we see other than this, the other methyl groups are that, which is environment B as well as environment D. We can use the splitting pattern, and as we can see, this one here is going to be split into a triplet since there are 2 hydrogens on the neighboring carbon. So using the n+1 rule, 2 + 1 gives us 3, so it's a triplet. And this environment here has 0 hydrogens on the neighbors, so it's going to be 0 + 1, meaning it's a singlet. So if you're using the splitting pattern, and then using relative peak area, in environment B we have 6 protons while environment D has 3. So the ratio of B to D is going to be 2 to 1. And then using the chemical shifts, if you look at this environment, it has HCC double bond O, which is going to be about 1.6 to 3.0 ppm. And then if we look at this environment, it's HCC, which is between 0 to 1.8 ppm. So they can be distinguished using their chemical shifts as well. In part C, they say an isomer of X is a carboxylic acid with 5 peaks in the carbon-13 NMR spectrum. Draw a possible skeletal structure for this carboxylic acid. Since it has 8 carbons, like we saw previously, and 5 peaks, the possible structure is this with 1, 2, 3, 4, 5, 6, 7, 8 carbons. And the environments are this, which is 1 to that, same as that, 2, then we go to 3, 4, and 5. Then next they say the painkiller aspirin is also an ester formed by the reaction of 2-hydroxybenzoic acid and ethanoic anhydride. So this is it. They say part of the mechanism for this reaction is shown. And they said add a single curly arrow to step 1 and a single curly arrow to step 2 to complete this part of the mechanism. Now for this mechanism, because we see O becoming OH with a positive, it means this is giving electrons to the hydrogen to create OH+, which we see there. And then in the next, we see a connection between oxygen and carbon, as we can see here with a positive charge. It means the oxygen is making a connection to this carbon, and so this lone pair is going to be given to the carbon. So this is my next curly arrow, and we create the product. Then next they say, state the role of H+ ion in the synthesis of aspirin. It protonates the oxygen in order for the reaction to be initiated. So I said the H+ ion acts as a catalyst by protonating the carbonyl group. Question 17, this question is about acids containing sulfur. Sulfuric acid reacts with sodium hydroxide solution as shown, which is this equation. This is calculate the pH of the solution formed when 20 centimeters cubed of sulfuric acid of concentration that is mixed with 80 centimeters cubed of sodium hydroxide solution which has this concentration. They want you to give your answer to 1 decimal place. So here I began by getting the moles of sulfuric acid, which is the concentration we have times the volume. Volume after being converted to decimeters cubed by multiplying by 10 power negative 3, and I got those moles. Then the moles of sodium hydroxide, which are going to be again concentration times volume, that times 10 power negative 3, giving us that. When we look at the equation, the ratio is 1 to 2, meaning the moles of sodium hydroxide that are required are going to be twice those of sulfuric acid, so which is 2 into 1.44 times 10 power negative 3. Therefore, the excess moles of sodium hydroxide are going to be the moles of sodium hydroxide which were provided, those, minus the moles of the sodium hydroxide which were required, which is that. Now we find the concentration of the excess, which should be number of moles over volume, this number of moles. But how do we know the volume? Remember, they used 20 and 80, giving us 100. Now the solution is 100 centimeters cubed in volume, meaning convert that to decimeters cubed by dividing by 1000. So when I use my calculator, I got 0.1632 mole per decimeter cubed. That is the concentration, and so pH should equal to 14 minus POH, since this is the hydroxide concentration. So negative log of OH minus ions gives me the POH. So 14 minus 0.79 gives me 13.2 as the pH. Then they say in part B, sulfurous acid, which is a weak acid and dissociates as shown. It forms a buffer solution when mixed with sodium hydrogen sulfide. State what is meant by the term weak in this context. If it's weak, then it means there is partial dissociation, meaning at equilibrium, very few moles of the acid have been dissociated. So I say that weak acid is one that only partially dissociates in aqueous solution, only a small fraction of its molecules ionize. Then state what is meant by the term a buffer solution. This is a solution that resists change in pH when small amounts of acid or base are added. You could say acid or alkali are added. Then they say calculate the mass of sodium hydrogen sulfide that should be added to 50 centimeters cubed of this concentration sulfurous acid solution to form a buffer solution of pH 2.18. They've given us the Ka for the acid and the relative formula mass of the acid. So I use pH is equal to pKa plus log HSO3 minus divided by the concentration of the acid. These two are concentrations. Since I'm given the pH and I have the Ka, I can find the pKa, which is negative log of Ka, plus the low concentration of this is unknown, but we know the concentration of sulfurous acid, which is that. And then we make this the subject. So this is what I got. Now to convert this part to this part, in logarithms, if something is divided, it's the same as saying the log of the numerator minus the log of the denominator. And all these are log to base 10. So 2.18 minus that equals that plus 1.3188. In collecting the known parts together, I got the log of the concentration of this equal to negative 0.9513. And to find the concentration is going to be 10 power that. And I got 0.11188 mole per decimeter cubed. So the concentration is that, and then mass is number of moles times MR. However, the number of moles is going to be concentration times volume. Since we know the concentration, I'm going to multiply by the volume. Remember the volume was 50, so 50 divided by 1000 to convert this to decimeters cubed, and then times the MR. I combine these two equations to generate this, so that it's easier for me to just substitute and get the answer. And so I got 0.582 grams to 3 significant figures. In question 18, this question is about carbonyl compounds such as ethanol. Ethanol reacts with a weak acid, hydrogen cyanide, to form a racemic mixture of hydroxynitriles, as we see here. They say a small amount of sodium hydroxide solution is also added to the reaction mixture. Complete the mechanism for the reaction, include Cayley arrows, the structure of the intermediate, and any relevant lone pairs and dipoles. So here the CN begins by connecting to the partially positive carbon, and then this bond is going to break. When it breaks, we see O- here, but the electrons from the bond went here and they formed this lone pair. So we see CN has attached to the carbon, and then hydrogen here and CH3. Then in the next step, these electrons are going to be donated to the hydrogen because this bond is polar, and that bond breaks, giving CN-. They say explain why a small amount of sodium hydroxide solution is added to the reaction mixture by considering the nature of the attacking species in the slow state. If we go back here, remember they're using hydrogen cyanide. Most of the time this reaction takes place when they use potassium cyanide in the presence of hydrogen cyanide. But here, the use of hydrogen cyanide, this is a weak acid that cannot donate the CN- in a higher concentration. So when they add sodium hydroxide, the hydroxide ion is going to use up the hydrogen generated in order to shift the equilibrium position towards the right so that more CN- can be generated. So I said HCN is a weak acid and only partially dissociates to give that. OH from sodium hydroxide removes the hydrogen, shifting the equilibrium position to the right. More CN- is formed, increasing the rate of the nucleophilic attack in the slow state. In B, they said it used the rate equation for the reaction using the mechanism in A1. So we saw the mechanism in A1, let's see here. There is a slow step and then the fast step. So we will consider things that occur in the slow step. So it's going to be that and that. Since one of each is taking part, so it's going to be rate equals to K, concentration of that, to power 1 times concentration of cyanide to power 1. Sketch a line on the axis to show how the concentration of ethanol affects the rate of this reaction. The rate is directly proportional to the concentration of ethanol, so it's going to be a straight line going through the origin. In part D, carbonyl compounds can be identified from their 2,4-dinitrophenyl hydrazine derivatives. Describe this process, including in your answer the observations you would see in the formation of the 2,4-dinitrophenyl hydrazine derivatives, an outline of the steps used to separate and purify the derivative, giving the purpose of each step, how the derivative is used to identify the original carbonyl compound. Detailed descriptions of the practical techniques are required. Now I'll begin with the observations. When we use 2,4-DNPH, we will observe yellow or orange precipitates. I usually say orange precipitates. Then to separate and purify, we will filter using a Bachner funnel in order to collect the precipitates that are formed, and then we will recrystallize by dissolving the impure solid into a minimum amount of hot solvent, and then upon cooling we will filter and then rinse the crystals with minimum amount of ice cold solvent. After, we can dry using filter paper in order to remove excess solvent, and if you want, you could also use a slow oven in order to get rid of the solvent. And then identification, we'll measure the melting points of the purified derivatives and compare with data book values of known derivatives of 2,4-DNPH to identify the carbonyl compounds. In question 19, this question is about the hydrolysis of halogen alkanes with hydroxide ions. The initial rates for the hydrolysis of 2-bromobutane were obtained for different initial concentrations of the reactants. Both 2-bromobutane and the product formed in this reaction exist as pairs of stereoisomers. So you can see the results here in the table. They say all the rates were determined at the same temperature. State what is meant by the term stereoisomer. This is a compound with the same structure formula as another compound, but with a different spatial arrangement of atoms. So next they say show that the data in the table are consistent with the SN2 mechanism for this hydrolysis of 2-bromobutane. If we go back here, we see when the concentration of this is doubled, this is kept constant, the rate doubles, so it's first order with respect to 2-bromobutane. And when this is tripled, that is multiplied by 2, here we see increase in the rate by a factor of 6. So this is going to be first order with respect to the hydroxide as well. I can show it here. If the original rate is rate equals to K into concentration of Rx per X times OH power 1, because we've already established this is order 1, it means the rate is going to be twice. If this one comes out, since it's power 1, we can bring it out into 3 Rx power X. X is the order of the halogen or alkane, the unknown order, times OH power 1. And this has increased 6 times. This means 6 is going to be 2 times 3. And so they should be also order 1, because 2 times 3 will give us 6 of the original rate. So here I said from 1 to 2, doubling the concentration of 2-bromobutane while keeping that of OH minus ions constant. The rate is doubled. So it's first order with respect to 2-bromobutane. And from experiments 1 and 3, tripling the concentration of 2, this should be of 2-bromobutane while doubling that of hydroxide ion, the rate increases by a factor of 6, so the rate is first order with respect to OH minus ions. Since both were present in the rate determining step and their orders are each 1, then the mechanism is consistent with SN2. Then they say in one experiment, a single stereoisomer of 2-bromobutane was hydrolyzed. Explain the stereochemistry of the product of this reaction. If it was hydrolyzed, the incoming nucleophile can only attack from one side because it's SN2. So I said SN2 reactions proceed via backside attack, meaning away from the leaving halogen. This leads to inversion of the configuration at the chirocarbon. Since a single stereoisomer of 2-bromobutane was used, the product will be the opposite enantiomer, which is the mirror image. Thus, the product has inverted stereochemistry relative to the reactant. In part B, they say 2-bromo-2-methylbutane, which is that can also be hydrolyzed with hydroxide ions. The mechanism for the reaction is SN1. The reaction profile is shown here. So here we see the first reaction, and then we see the intermediate, and then we see the products being formed. So there is some stability of the intermediates. This explains how all the features of this reaction profile are consistent with an SN1 mechanism. Like I said already, this is process going through 2 steps, meaning it's SN1. So SN1 reactions proceed via a 2-step mechanism. The first peak represents the slow formation of the carbocation intermediate, which is the rate determining step. The intermediate is going to be there. And the second smaller peak represents the fast attack of the OH ion on the carbocation. The intermediate carbocation is stabilized by alkyl groups because tertiary carbocation. The overall energy profile is consistent with SN1 due to the 2 activation energies and a stable intermediate. In question 20, this question is about group 2 compounds. Barium carbonate decomposes at high temperature as shown, we see there. Calculate the standard entropy change for the system. They've given us the information in the table, and we know the S system equals the total product entropy minus the total reactant entropy. So product entropy, we have 70.4 plus 213.6, and then we subtract the reactant entropy, which is that, to give us positive 171.9 joule per Kelvin per mole. So next they say the lowest temperature at which barium carbonate decomposes is 712. Use this information in your answer from A1 to calculate the standard enthalpy change of the reaction in kilojoules per mole. So ds total equals to 0 at that temperature, so ds surroundings equals negative ds system. And since we have ds system, getting the negative of that, I get that. So since ds surroundings equals negative delta H over T, delta H will equal to negative temperature times ds surroundings. We know the temperature is 712, so add 273 to create the temperature in Kelvin times the value we have as ds surroundings. In my calculated answer gave me positive 169,300 joule per mole, which is the same as 169 kilojoules per mole. Then they say magnesium chloride is used in the manufacture of tofu from soy milk. An experiment was carried out to determine the enthalpy change of solution of anhydrous magnesium chloride. 4.26 grams of anhydrous magnesium chloride was added to 200 centimeters cubed of the ionized water in a polystyrene cup. The mixture was stirred to ensure all the solid dissolved to form a solution. The temperature of the solution rose by that. They say calculate the enthalpy change of solution of anhydrous magnesium chloride. Include a sign and units in your answer. So we have this as the mass of the solid. We'll use this to calculate the number of moles. And since this is the volume of the solution, we're going to use it as the mass in this formula. So mass, delta T, and the C. So Q will equal to 200 times 4.18 times 6.8, giving us 5.684 kilojoules. And then the moles of magnesium chloride, I use the mass here, divided by the molar mass of magnesium chloride to get the moles, and they give me that. So to calculate delta H for the solution, it's going to be the Q we have here divided by the number of moles, but this is an exothermic reaction, so we'll put a negative, and I got negative 127 kilojoules per mole after rounding off to 3 significant figures. Then part C, the standard enthalpy change of solution of anhydrous magnesium chloride, which is a solid, can also be determined using a Hess cycle. Complete the Hess cycle shown by adding appropriate formulae with state symbols to the empty boxes. Now, if it's lattice energy, meaning we are forming a solid, so from gaseous ions, so this should be Mg2 plus 2Cl minus to give us the solid. And of course, hydration, these are going to become aqueous, and this is going to be solution again from solid to aqueous. So here they've given us the lattice energy that and the standard entropy change of hydration of magnesium ions as that. Then they say calculate the standard enthalpy change of hydration of chloride ions using the cycle and data in C1 and your answer to B. If you do not obtain the final answer to B, use this value. This is not the correct value. So the enthalpy change of solution is equal to, I used this part here, this is equal to negative of that plus that. So the solution equals negative lattice energy plus the hydration of magnesium, which is 1 magnesium ion, plus twice because chloride ions are 2. So making this hydration the subject, it's going to be the enthalpy of solution plus lattice energy minus hydration energy or enthalpy of magnesium divided by 2. Then I substituted the values. This is what I calculated, negative 127. And then this is the lattice energy given to me. And this is for the hydration of magnesium. Dividing by 2, and I got negative 366.5, which is about negative 367 kilojoules per mole. Then part D, the theoretical lattice energy for magnesium chloride is that give 2 assumptions used in theoretical calculations of lattice energy. Here we assume they're perfect spheres touching each other, and there is pure ionic bonding. So I said the ions are treated as perfect spheres in contact with each other. There is 100% ionic bonding and no covalent character, purely as a result of electrostatic attraction between the oppositely charged ions. Then explain the difference between the theoretical and experimental values for lattice energy of magnesium chloride. The theoretical values assume pure ionic bonding, like we already saw. However, the experimental value is more exothermic due to partial covalent character resulting from polarization of chloride ion by the small, highly charged Mg2 plus ion. Then part E, hydrated barium chloride is a soluble toxic salt. It can be formed from the reaction of barium carbonate with hydrochloric acid as shown. So this is the reaction. They say a 5-gram sample of barium carbonate reacted with 120 centimeters cubed of 0.5 mole per decimeter cubed hydrochloric acid. Show that the hydrochloric acid is in excess. So let's begin by getting the moles of barium carbonate. Moles of barium carbonate, we need the mass and the molar mass, but we need to find that. So molar mass of barium carbonate, this is for barium, that is for carbon and the 3 oxygens. I got that. So then moles of barium carbonate will be the mass divided by the molar mass, giving us that. And then the moles of the acid, concentration times the volume. Of course, the volume in decimeters cubed, you get 0.06 mole. But when we look at the equation, the ratio should be 1 to 2, meaning hydrochloric acid moles should be twice the moles of barium carbonate. So these moles of barium carbonate will require 2 times that of HCl, which is basically this. However, when we compare, we have more than required, so HCl is in excess. And then they say all of the barium carbonate reacted and produced 6.19 grams of hydrated barium chloride. Calculate the relative formula mass of that and hence deduce the value of N. So from the equation, of course, previously we already know the moles of barium carbonate. We've calculated them as that. Because the moles of barium carbonate equal to the moles of this whole compound, they are the same number of moles. So the molar mass of barium carbonate, NH2, is going to be mass divided by the number of moles. So the mass given is 6.19 divided by the number of moles, and I got that. So this is the molar mass of the product. And from here, I'm going to subtract the composition from barium chloride. So from barium chloride, its composition is 208.3. You would say the molar mass contribution. So that minus that gives us the remaining part, which should be corresponding to NH2O. So giving us 35.96. And so 18N, water is 18 times N. So 18N equals to that. Divide by 18, I got 2. So the value is approximately 2. So this brings us to the end of question 20, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.